Hello students, welcome back. Today we will study a very important topic of chapter 1, electric field and charges. The name of the topic is Gauss law. Okay, now this is very important topic. Gauss law gives us the formula for flux, electric flux over a closed surface, and it has an application to find out the electric field. Okay, so first we'll find out the formula that gives the Gauss, that is given by the Gauss law, that is about the flux. Okay, and then we will see how the Gauss law is useful for finding the electric field. Okay, so after that we are going to study about the application. Okay, so first to find out the formula for Gauss law, we need to take a closed surface. Okay, so let's take a closed spherical surface. Okay, I have taken a spherical closed surface. Now let's take a charge Q. I am taking a charge Q inside that spherical surface. Okay, so now I have to find out the total flux through this closed surface. Okay, let the radius of this spherical surface be r. So what I will do, I will select a very small area element, surface element. Okay, so let's select this small area element dA. Okay, I have selected a small surface element, surface area element dA. Now the electric field at that point, okay, as let's take this as the positive charge, so it will be directed outward. So this is the direction of electric field at that point. So the angle between E and dA, that is equal to 0. In this case, angle theta is equal to 0 degree. Angle between E and dA both is 0. Okay, so now what I will do, I will find out a small amount of flux. Okay, I will find out a small amount of flux passing through this area. Okay, so first let's do that. Okay, so d phi, I will write down d phi because I'm only finding this flux through this much area. So what is the formula for flux? Flux, electric flux, number of electric field line passing through any surface normally through it. Okay, so it was E dot A. So what is the electric field? E. And what is the area? dA. So it is a dot product E dA cos 0 because the angle between E and dA is 0. So this will be equal to EDA. So what we had done, we had found out a very small area. We have selected a very small area element and we have found out the flux passing through this area. Okay, so the small amount of flux passing through this limited area, selected area is EDA. So if I need to find out the total flux, then what should I do? I should integrate d phi. Means I will integrate all these small dA element, the electric flux passing through all these small area element. Okay, so integrating it, we will get integration of EdA. Okay, electric field. See, now if I am taking here, this is R. Everywhere the distance from this charge is R, right? So electric field at every point on the surface is same. So E is constant. So this will be equal to E integration of dA. Now integration of dA, what is the total surface area of a sphere? because we have taken this spherical surface, right? So the total surface area of a sphere is 4 pi r square. So this is equal to E into 4 pi r square. Clear? Electric flux is equal to E into 4 pi r square, right? Now, what is the formula for electric field? If I take the point electric field at here, formula for electric field is kq by r square, or I can write down 1 by 4 pi epsilon 0 q by r square. Okay, so this was the electric field at every point on the surface. So putting this value, I get 1 by 4 pi epsilon 0 q by r square into 4 pi r square. So 4 pi r square gets cancelled, and that implies flux is equal to q by epsilon 0. Okay, so this is Gauss's law. In fact, it's summation of q by epsilon 0 means if there are more number of charges inside that closed surface, then the flux will be summation of total charges enclosed inside this surface. So summation of q by epsilon 0. Okay, where summation of q is the total number of charges or the total charges enclosed inside the closed surface. Clear? So if I want to state this Gauss law, then you can say that the electric flux passing through any closed surface. Remember, we have taken closed surface, sorry, spherical surface. But this is true for any closed surface. You can take any closed surface. You can take cubical surface, cylindrical surface. For any surface, this law holds true, right? So, if you want to state it, Gauss law, then it is the total flux passing through any closed surface is the ratio of the total charge enclosed inside that surface to the permittivity of free space. Okay, so this is Gauss law. So I'm repeating the whole Gauss law once again. Remember, so this is very important topic. Okay, see what does Gauss law gives? Gauss law gives us the total electric flux passing through any closed surface. So first, what type of area we have selected surface? We have selected spherical surface, and we have assumed there is a charge plus q at the center of the surface, right? So electric field at every point on the surface will be kq by r square or 1 by 4 pi epsilon 0 q by r square. Okay, now we have selected a small area element dA, and the angle between E and dA is 0. So the small amount of flux passing through this is EDA cos 0, that is EDA, right? So this is small amount of flux d phi. So the total flux will be integrating, we will integrate this small amount of flux. So we get integration of EDA, the E is constant, integration of dA, the total surface area 4 pi r square, putting the value of E, we get finally flux equal to Q by epsilon 0. Okay, so just go through this topic, that is Gauss law. Okay, now some important points related to Gauss law. Okay, so what was this? Q by epsilon zero. Okay, so first, Gauss law is true for any closed surface. So I'm writing in short, true for any closed surface. Remember, the Gauss law is true for any closed surface, not only spherical, but it is true for any closed surface. The second point, when we are writing flux equal to Q by epsilon zero, what does this Q means? Total charge enclosed. Okay, Q means total charge enclosed inside the surface. So if I am taking such type of surface and there are some charges Q1, Q2, Q3, Q4 and Q5. Okay, now what will be the formula for flux? You can say that flux will be equal to Q1 plus Q2 plus Q5 upon epsilon zero. That means summation of which charges? The charges enclosed inside the closed surface. Okay, but when we are calculating electric field, when we are calculating electric field, all charges are taken. Remember, when you are calculating the electric field, then all the charges are taken, right? Means when we are calculating flux equal to E dot dA, right? Then all the in that term E electric field, all the charges are taken. But when you are using this formula, summation of Q by epsilon zero, then this Q is only the total charge enclosed inside the closed surface. Okay. The fourth one is about Gaussian surface. Okay, the fourth one is the area that you select, right? The surface area or area that you select. Means here we had selected spherical area. Then that area is called Gaussian surface. Okay, if I select an area like this, cylindrical surface. Now the charges are here. Q1, Q2, Q3. Then this surface is the Gaussian surface. Okay, if I select an area like this, the charges are here, then this surface is called Gaussian surface. Okay, so that means the area that we are selecting to calculate the flux using Gauss law, that is called Gaussian surface. Okay, so these are the four important points related to Gauss law. So just go through these points. Okay, now moving to the next point. Now, the next point is applications of Gauss law. Okay, as before discussing this topic, Gauss law, I have already discussed that this is useful in finding the electric field. Okay, so our first application is we can find the electric field due to infinitely sized, long, uniformly charged wire. Okay, so first is field due to long uniformly charged wire. Okay, so now what we are taking, I am taking a long size wire. Okay, and okay, the charge is uniformly distributed. The word uniformly distributed means the charge linear charge density is same. It's not that at this portion there is higher amount of charge and the same length of this portion there is less. Okay, so if you cover the same length, any area, the charge amount of charge is same. So this is uniformly, okay, uniformly charged wire. Clear? So this is we studied this in linear charge density. Okay, so let linear charge density equal to lambda. Okay, and we are taking lambda is equal to Q by L. Okay, where L is the total length of wire. That is linear charge density. Okay, so now how we will find out the electric field? I want to find out the electric field at this point P. Okay, I want to find out the electric field at this point P. So what I will do? I will select a Gaussian surface. Which type of surface? Cylindrical Gaussian surface. Okay, so now, okay, I have selected a cylindrical Gaussian surface. I want to find out the electric field at this point P. Okay, so what I will do, I will select a small surface area dA, right? I will select a small surface area dA. Clear? And the electric field due to this positive charge, it will be in this direction. So the direction of electric field will be also in this direction. So now what is the angle? The angle between E and dA is 0 in this case, right? When I take electric field at this direction, okay, if I take any area here, then the area vector will be in this direction, the electric field direction will be in this way. So the angle is 90 degree, right? So the flux, the total flux E dA cos 90, that will be equal to 0. Same way, if I take this area, then again this will be area element, okay, and this is the electric field, again 90 degree. So here also the flux is equal to 0. But in this case, the angle here theta is equal to 0 degree. So the electric field at this point, okay, or over this cylinder, okay, that will be equal to flux equal to E dA cos 0, right? Integration of E dA, right? The total flux, I am taking the total flux E dA cos 0. Okay, I can write it down like phi 1 plus phi 2 plus phi 3. Right? So the total flux will be equal to phi 1 plus phi 2 plus phi 3. But this two, the flux is 0. So only remaining is at this position. So this will be at that E dA cos 0. So cos 0 is 1 E integration of dA. Right? So now what is the total surface area? Total surface area of this cylinder. Not total, cylindrical. Okay, curved surface. We will take curved surface area. We will not take these two area. We will take curved surface area. So the formula for curved surface area of cylinder is 2 pi r L. So if I take this as the radius, okay, then this will be equal to E into 2 pi r L. Clear? Means this distance I have taken as L. The total length was L. Now this smaller. So E into 2 pi r L. This is the total flux. But what does the Gauss law say? We had heard that formula. Flux is equal to Q by epsilon 0. Right? Now what will be the charge? Right? So Q will be equal to lambda into L. This we had discussed in linear charge density. If the linear charge density is lambda, then the charge on a particular length L will be lambda L. Right? See, lambda equal to Q by L. For complete length, it's lambda. For L, it's lambda into L. Right? So this is the charge. So lambda L by epsilon 0. So this name this equation 1, equation 2. So these are the two equations that we are getting for flux. First using E dot dA, second using Gauss law. So both will be same. So E into 2 pi r L equal to lambda L by epsilon 0. So length gets cancelled. So what is the electric field? Lambda upon 2 pi r epsilon 0. Clear? So electric field at any point at a distance r, at a perpendicular distance r from that wire, okay, from of a long wire, it is lambda upon 2 pi r epsilon 0. Clear? So this is electric field. Now, what I can do arrangement, multiply by 2, divide by 2. So what is this? 2 into 2, 4 pi epsilon 0. 1 upon 4 pi epsilon 0, that is K. So electric field will be equal to K. Now what is remaining? Lambda by 2K lambda by epsilon 0. Clear? So the formula for electric field for a long uniformly charged wire is E equal to 2K lambda by epsilon 0. Clear? This is the formula for electric field. I am repeating this topic once again. Okay, so what we had done, we had taken a long wire, uniform charge, total charge Q, total length L. So the charge density lambda will be equal to Q by L. Okay, now we have to find out the electric field point P. So we have selected a cylindrical surface, right? So now there are three different types of surface. One, this, and second, and another is curved surface. The electric field due to these two surfaces, zero. Sorry, the flux due to these two surfaces, zero, because the direction between electric field and area is 90, so zero. So the only thing remaining is flux due to this curved surface area, right? And here the angle is zero. So this is equal to integration of E dot dA, EdA, and which dA we are taking? We are taking only d of curved surface, that is E into 2 pi r L. Okay, using Gauss law, Q by epsilon 0, where Q is lambda L. Equating these two things, finally we get E equal to 2K lambda by epsilon 0. Clear? So just go through this first application of Gauss law. Clear? And what is that? Electric field due to long uniformly charged wire. Okay, so go through this. Okay, you can also use this formula, lambda by 2 pi r epsilon 0. And you can also use this. You can use any one of that. Okay, so this was about the first application. Okay, for today, that's it. Okay, for in our next video, we will see the remaining two applications. Clear? In that application, we will see that the electric field due to uniformly charged long surface, okay, planar long surface, okay, and the second one, uniformly charged spherical cell. In that spherical cell, we'll find out the electric field outside the cell as well as inside the cell. Clear? So this was about the application of Gauss law. Okay, thank you.